Hello, we are from SKE3533 Session 3 Group 5. Today we will present on frequency modulation. Our group members are Chu Yubing, Yo Jihong, Annie Lau Hing Wan, and Yong Chen Sun. Let's begin with frequency modulation of FM. FM is a type of angle modulation first introduced by Edwin Armstrong in 1931. Unlike AM, which changes amplitude, FM varies the frequency of the carrier to improve noise performance. Because the amplitude stays constant, FM is far more resistant to interference. That's why FM became the backbone of clear radio broadcasting, emergency communication, and even medical telemetry. FM is everywhere in our daily life. For example, when you switch on the car radio, you turn it into a specific FM station frequency. The receiver then demodulates the FM signal to recover the original audio, giving you clear music or speech. Modern radio even display more information through RDS or radio data system such as song title, traffic alert, and emergency message. From everywhere entertainment to critical communication, FM continue to shape how we connect and stay informed.
First, this is the equation of FM signal, where Kf is the frequency deviation constant in radians or second or volt. Assuming that the modulating signal Vmt as the equation shown here, when we substitute the modulating signal into the equation, we will get a more practical form of FM signal, which is the equation shown here. From this, we can define the maximum frequency deviation, usually written as delta omega, which represents how far the instantaneous frequency moves away from the carrier. Next, we introduce the modulation index beta. This is an important parameter defined as the ratio of maximum frequency deviation to the modulating signal frequency. A higher modulation index means the carrier frequency swings further from its central value. The equation here is the FM equation. It's also known as the wideband frequency modulation, which is the equation shown here. When we explain the FM equation, we can see that FM produces a carrier component at carrier frequency and multiple sideband at frequency Fc plus n FM, where n is an integer. Unlike AM, FM theoretically produces an infinite number of sidebands. However, the number of significant sidebands depends on the value of beta. To determine how many sidebands are meaningful, we use Bessel function table, which show the amplitudes Jn times beta. This value indicates how many power each sideband carries. As beta increases, more sidebands carry significant power. This slide shows an example of FM spectra. We can observe that the bandwidth increases when beta increases because more sidebands appear. The Bessel function plot also shows the magnitude of the carrier decrease as beta increases, since more power is distributed into the sidebands. The amplitude of the frequency spectrum depends on the value of Jn times beta. Now, to estimate practical bandwidth of FM, we use Carson's rule. Even though FM has infinite sidebands, experiments show that transmitting the sidebands up to 1 plus beta is sufficient to cover 98% of the total power. Therefore, the required bandwidth is approximately 2 times delta F plus FM. Now, moving to the real device that generate an FM signal. A common example is the FM car transmitter. This device is often used in cars that do not have Bluetooth or a US input. The transmitter connects to a phone usually through Bluetooth, and then it modulates the audio onto an FM carrier frequency such as 98.3 MHz. When the car radio is tuned to the same frequency, it receives and demodulates the FM signal, allowing the audio to be played through the car speakers. This shows how FM modulation is used in a simple everyday application. Now, we look at the characteristic of the FM signal produced by such a device. The first characteristic is constant amplitude. In FM, the amplitude of the carrier stays the same at all times, and only the frequency changes in response to the audio signal. This makes FM more resistant to noise because most noise are from amplitude, but not frequency. The second characteristic is that the signal contains a carrier and multiple sidebands. The carrier is fixed at a certain frequency, while the sideband appear at frequency Rin, separated by the modulating frequency. These sidebands carry the actual audio information. When the audio signal becomes more complex or contain more frequency, the number of sidebands increases as well.
Now let's take a look about how is FM generated. Basically, there is 3 types of method to generate the FM signal. The first is direct method, second is cross-beam method, and third is indirect method. For direct FM generation, first we have the varactor diode. A varactor is a diode whose capacitance changes with voltage. When the modulating signal changes the diode's capacitance, the LC circuit frequency will also change. Second, reactor modulator. A reactor modulator makes a transistor behave like a variable capacitor or inductor. It is placed across the LC circuit of the oscillator, and as the transistor reactor varies with the audio signal and the oscillator frequency shift. Third, voltage controller oscillator, which is a circuit where output frequency is proportional to input voltage. If the message signal is fed into the VCO input, its frequency will continuously change. For varactor diode FM modulator, there is an LC oscillator which can produce a frequency which is depend on the capacitance, which is depends on the input voltage. So when the message signal voltage change, the capacitance will also change. For Crosby FM generator, actually is also a type of direct method, but with the add of the use of the technique that can prevent the frequency shift problem by using an automatic frequency circuit to produce stable FMs, which is suitable for real transmitter. For AFC circuit, there is a discriminator which can monitor the output frequency. If the frequency drift, it can create an error voltage. This error voltage can feedback and correct the oscillator. This technique is used in communication system where stability is important, such as FM broadcast station. For indirect FM generation, which involve Armstrong method that indicate generate FM signal by creating PM signal first and then converting it into FM. Basically, for Armstrong method, it will involve a crystal oscillator to provide highly stable carrier frequency for the initial low frequency phase modulated signal. Armstrong method can produce two types of frequency modulation signal, which is narrowband FM signal and wideband FM signal. Easy to understand, the MBFM is usually used small frequency change to save bandwidth suitable for voice communication system. WBFM is always used larger frequency change to deliver high quality sound and ideal for broadcasting.
Have you ever wondered how your car radios turns those invisible waves in the air into music you can hear? Okay, so after the FM signal is generated, a receiver has to decode it. It listens to the tiny frequency changes and converts them back into the original sound. The simple hidden process is called FM demodulations. There are two main ways to do this, the discriminator method and the phase lock loop method. The first method is the discriminator, also known as loop detection. Basically, this method converts frequency changes into amplitude changes. After that, an error detector extracts the original waveform. Discriminator circuits are simple and low cost. That's why they are commonly used in older FM radios. So for the mathematically part, firstly, FM signal with lots of noise in the air is caught by antenna and enters a hard limiter, which aims to remove the noise. It will then pass through a bandpass filter tuned to the carrier. This keeps only the part of the signal we actually need for demodulations. After that, the signal goes into a differentiator. That's where FM turns to AM signals. An envelope detector picks up the amplitude shape, which actually represents the message signal, or we call it as original audio. Finally, a DC block removes any leftover offset, leaving just the clean message signal we want to hear. The second method is the phase lock loop, or we call as PLL, which mainly used in modern radio or car radio nowadays. PLL works by locking onto the instantaneous phase of the FM signal. When the signal's frequency change, the PLL produces a corresponding voltage, which directly represents the message. That's why they are highly stable, accurate, and widely used. Also, they work well even with weak or noisy signal. Now, why does all this matter to the community? FM communication is more resistant to noise than AM, making it dependable in environment with interference. This is why emergency services like police, ambulance, and fire department rely on FM for clear communications. Even in rural areas, FM broadcasting is a reliable way to spread public information during emergency. There are also a few common misunderstandings. Many people think FM use more power, or seems like an old technology, or even FM is only for music, but in reality, the power stays constant while the bandwidth increases. It also remains important in modern chip and communication modules, which used for safety communication and everyday wireless device.
As a conclusion to this session, FM is widely used in ways we all experience daily. Software-defined radio made broadcasting flexible and affordable. Low-power FM oscillator power IoT sensor and medical wearable, saving energy. Digital pre-distortion produce clearer signal and improve spectrum use. AI-based monitoring detect illegal transmitter and enforce safety. This innovation made FM more available, efficient, and secure today. Of course, misconceptions exist. Some believe FM signals are harmful to health, but they are not ionizing and safe under regulation. Others think FM interference with aircraft system, but licensed stations follow strict allocation. Interference only comes from faulty or illegal transmitter. Broadcasting also requires proper license, since unlicensed FM can cause harmful interference. Finally, while FM has theoretically infinite sideband, concern rules so that most of the signal power is confined within a finite bandwidth. Finally, let's consider the societal impact of FM. In emergency, FM link can be deployed quickly, saving lives. In healthcare, FM telemetry support patient monitoring and medical wearable. In education and culture, FM broadcasting deliver clear audio to school and community. And with clearer transmitter and monitoring tools, FM ensures spectrum efficiency and fair access for all users. Altogether, FM continues to play a vital role in connecting the people, protecting life, and enriching society. Thank you for listening to us, and don't forget to join our FM small quiz and fill out the service learning evaluation form in the description of our video.